Okay, we've learned that the silicate minerals are important and comprise most of the Earth's crust, including both the continental and oceanic crust. And those silicate minerals can be divided into some main silicate subclasses that group the minerals into similar crystallographic structures. And those subclasses also share many physical and optical properties within them, and will help us to identify minerals and to understand the chemical composition of the minerals and to remember their mineral formulas. For instance, the framework silicates, or the tetrahedra that include the very important feldspars and quartz, have a silicon to oxygen ratio of 1 to 2. And that is that they form tetrahedra of silicon and oxygen, with the silicon ion in the center of 4 oxygen ions. And those tetrahedra form a complex network of tetrahedra in the tectosilicate group. And all the silicate minerals have these silica tetrahedra within them, and they are simply bonded to each other and to the cations in different ways. The tetrahedra, you'll see, has these negative oxygen ions on the outside of the tetrahedron, and those bond to the cations in the minerals like calcium, magnesium, sodium, iron, that give us the different chemistries of the minerals within those subclasses. All right, so tectosilicates are forming these complex networks. Another group are the sheet silicates, or they're also called the phyllosilicates. And those form sheets of the tetrahedra. And then between the sheets of the tetrahedra, like if you think of a mica or a sheet of biotite, the cations are in layers in between those sheets of silica. Those have a consistent silicon to oxygen ratio of 4 to 10 or 2 to 5. And they're also hydrous, so they have a hydroxyl group in them. The next group are the single chain silicates, and there are two kinds of chain silicates. There's a single chain and the double chain silicates. The single chain silicates are the pyroxenes, and the double chain silicates are the amphiboles. You'll see they're both in this group of Inosilicates, standing for chain silicates. And the pyroxene group, or the single chain Inosilicates, have a silicon to oxygen ratio of 2 to 6 or 1 to 3, and that'll help us remember the formula for those minerals. In this case, the tetrahedra are lined up in a chain. In the double chain silicates, the amphiboles, they have a different silicon to oxygen ratio of 8 to 22 or 4 to 11, and those are also hydrous minerals, so they have a hydroxyl group at the end of them. And those are forming linked chains of silicon tetrahedra. The next group are the ring silicates, or the cyclosilicates. Those include tourmaline, which you'll remember by its horrendously long formula. And those have a silicon to oxygen ratio of 6 to 18 or 1 to 3. Then we have isolated tetrahedra. So Nesosilicates is how I often refer to them, and those include olivine, and those have a silicon to oxygen ratio of 1 to 4. And finally, the last group that I'll talk about are the sorosilicates, that are pairs of tetrahedra. And I'll show you some examples of more common minerals than this, but they have a silicon to oxygen ratio of 2 to 7. All right, the nesosilicates. These include olivine, that is common in igneous rocks, including periddotites, basalts, and gabbros of the oceanic crust and the mantle. They include topaz, starlite, the aluminosilicates of andalusite, sillimanite, and kyanite. Those are important metamorphic minerals, as is starlite and garnet. The sorosilicates are the paired tetrahedra. They include a common metamorphic mineral called lawsonite that occurs with glaucophane in subduction zone rocks. And they include epidote, which is found in metamorphic and igneous rocks, particularly when calcium is an important component of those rocks. The cyclosilicates. These are ring silicates, and there are fewer of these than some of the other mineral silicate subclasses. These include beryl and tourmaline. Tourmaline you'll recognize, and it's a common accessory mineral, meaning it occurs in small amounts in pegmatites and other granitoid rocks. The inosilicates, the chain silicates, include the pyroxenes and the amphiboles. Here we're talking about the single chain inosilicates, the pyroxenes, and those include both the clinopyroxenes and orthopyroxenes, and are commonly found in igneous rocks. Here's some augite, for example. The peroxenoids include wollastonite, which is a calcium-rich pyroxene that you find in more calcium-rich rocks, and also in metamorphic rocks sometimes. The double-chain silicates are the amphiboles, and those include commonly hornblende in igneous rocks and glaucophane in metamorphic rocks. And those are important constituents of the rocks that we'll look at in this class. The phyllosilicates, or the sheet silicates, include the micas of muscovite and biotite, very common in igneous and metamorphic rocks, particularly muscovite and metamorphic rocks. And the clay minerals that we'll see a few of, but you'll see more of those in said strat. The phyllosilicates also include serpentine, which is an important alteration mineral that you find in metamorphic rocks, particularly metamorphosed ultramafic rocks from the mantle or part of the lower oceanic crust. Chlorite, which is also a metamorphic mineral, it's an alteration mineral that oftentimes replaces other iron and magnesium bearing minerals like garnet or biotite. And talc. So, for example, I alluded to the silica tetrahedra having a negative charge and being bonded to the cations. In this example of a sheet silicate, or the mica group, we have muscovite on the left here, and look at the lower left, and you'll see a sheet of silica tetrahedra bonded to the black hydroxyl ions, the cation layer with aluminum and magnesium, followed by another sheet of hydroxyl ions, more silica tetrahedra, and finally the potassium in the muscovite. And that pattern is repeated to form the different layers of the muscovite. All right. As I said in the last lecture module, the feldspars are very important in both the continental and oceanic crust, and comprise almost 60% of the continental crust. These framework silicates are those more complex networks of silica tetrahedra, but include really important classes of minerals, including quartz and feldspar groups, and to a lesser extent, some more clay minerals or low-grade metamorphic minerals. We can relate the silica subclasses to Bowen's reaction series, and I hope you've seen Bowen's reaction series before. This is a series of minerals that crystallize from, let's say, a partial melt of the mantle, or basalts that come out of the mantle, and they come out at their highest temperature as melts, and as they cool, they crystallize. And Bowen's reaction series describes the order in which minerals crystallize, from the highest temperatures up at the top of Bowen's reaction series down to the very last bit of melt left, when the melt is at the low temperatures. And what we see is that olivine and pyroxene and amphibole are the first to crystallize out, along with the more calcium-rich plagioclase feldspars. And then as the melt cools, you get biotite and more sodium-rich plagioclase feldspars. Then the potassium feldspars, muscovite, and quartz, with continued cooling and crystallization. And that relates to the silicate subclasses, because the first minerals to crystallize out of the melt are the simpler silica subclasses. So the isolated tetrahedra crystallize first, then the chains of tetrahedra in the inosilicates, then the sheet silicates, and then down into the tectosilicates that are more complex. And that's side by side with this continuous reaction of calcium to more sodium-rich plagioclase feldspars crystallizing out. And so what I hope you get out of this, out of organizing the silicate minerals into these subclasses, is a way to organize in your mind groups of minerals that share similar physical and optical properties, and realizing that they have a regular and predictable silicon to oxygen ratio, and whether they have hydroxyl groups, whether they are hydrous mineral, that will help you to remember their chemistry and their mineral formula. Okay, in this module you learned that the silicate minerals are divided into subclasses based on their crystal structure, and that the minerals in these subclasses have similar physical and optical properties, that the silicate subclasses have a consistent silicon to oxygen ratio, and that the similarities within the different subclasses are going to help you to identify minerals and remember their chemical composition and their mineral formulas.